Hello, everybody, and welcome to our next package demo. It is getting to be a pretty late evening here in Boston, but good morning and good afternoon to all of our attendees across the world. We have Nitesh Turaga, who is a scientist in the Department of Data Science at the Dana-Farber Cancer Institute. And I'm going to hand it over to him because I know he's got a lot to tell you tonight.
Hi, everyone. I'm Nitesh, and let's start with some slides. So I'm going to share my screen first, and hopefully you all can see my screen. And I'm going to move this AirMeet thing on my side screen. Okay, so I'll start with some slides, introduce the topic, and we'll get into the demo from there. Right. So I'm going to be talking about BioC K8s Redis. It stands for Bioconductor Kubernetes Redis. It's an on-demand parallel computing Kubernetes application for Bioconductor users. These are some links to a couple of resources. The first one is to the slides I'm presenting to you guys right now. And the second one is the GitHub repo for the Helm charts. I'll explain what they are for the Kubernetes applications. This link right here is also clickable if you want to do that, and it'll take you to, the wrong link. So I'll have to update that, but this link still works. That's my bad. So follow this link, do not click on that. Right. So let me introduce what's happening here, first of all. Why are we doing this? So if you think about Bioconductor versus time, right? So Bioconductor started around 2001, and people used to run R on their local hardware, so their Macs and PCs back in the day. And the data size for genomics was small enough that it could fit onto their hardware. So they were able to do everything in R just fine. And then as data size kept increasing, it's more linear than this. I blocked it off in a way, but like it's a little more linear compared to this. And 2010 onwards, I want to say the number might be wrong, the year might be wrong here, but around that time, people started using more and more like virtualized infrastructure. And what do I mean by that? I mean, people started using high performance computing clusters at their institutes and like VMs on like the first cloud services, public cloud services available to people on Amazon and some public clouds. And then data size kept increasing even more. It kept getting bigger and bigger and bigger as sequencing became cheaper. And now I feel like we're running out of space and we have all of this data and not enough compute power. So this is where containerized applications come in on cloud services, which are cheaper and theoretically infinitely scalable. So, and that's the era we're in right now, right? So from 2016 onwards, Bioconductor started developing Dockerized applications, which can be deployed on the cloud. And again, like I said, should be scalable for users. So why are we using this? So like I explained before, so the data size is becoming larger. Not everyone has access to high performance computing resources. So at most institutions, people struggle with like time, or they have to share the time with other people, or they don't have enough compute capacity to run their jobs. And also cost, right? So a lot of institutions do not have access to high performance computing. So they struggle with like installing one. So it's almost always cheaper to just use cloud resources. You pay for what you want, when you want it, and you get access to it. So we've spoken about parallel computing, and I feel like now we need to introduce like how this basic parallel framework or the MapReduce framework works in R and Bioconductor. So lapply is the most basic MapReduce function in R, and it works in a very easy manner. So this R function works on a list of elements, and you supply a function to it. You can write whatever function you want, which works on one single element in that list. And that function lapply will apply to every element in the list for you. And in BiocParallel, we have a similar approach. It's called bplapply. So BiocParallel lapply. And the function signature is very similar to lapply. So you have a list of elements X, and you have some function you write, which you can apply over this list of functions. But then there's this special parameter at the end called bparam, which stands for BiocParallel parameter. And there's numerous approaches available for parallel computing. So you can do it in a multi-core manner. You can do it serially. You can use batch tools param. Like, I mean, you can use different kinds of parallel computing frameworks. And BiocParallel lets you use whichever one you choose when you want it. And you would usually use something like batch tools param, which is applicable to clusters with formal schedulers. And you can just plug in the function you want here, and you can still use this bplapply function, which is very familiar to Bioconductor users. So we try to stick with that familiarity when I introduce Kubernetes and like how we do parallel computing on Kubernetes. The goal is to stick to that familiarity. So what is this standard parallel computing model, right? So this is you, in case you're wondering. It's late at night, everyone's tired. So this is us right now, right? So, and this green box right here is this high performance computing cluster available at your local institution. And you connect to this head node through your local PC or Mac or Ubuntu machine or whatever local hardware you're using. And you're able to distribute your work through some workload manager in your HPC cluster. And there's many workload managers, right? There's Slurm, SGE, OpenGrid Engine, LFS, and so on and so forth. So you can use any one of these, whichever your institution uses, distribute your work, and there's a file system behind it to back it all up. So this is how standard parallel computing models work at most institutions. And there's some issues with this, right? So you have to be at a well-to-do institution more often than not to have access to something like this. And unfortunately, these institutions with HPC clusters are very limited. And then there's wait times, even if you do have it, right? So you have to wait for your colleagues to finish their jobs before you can get your jobs running. And whenever you want to install a new piece of software, you have to ask your sysadmin to install that software before you can get it running on your machine, on your HPC framework. And each worker here, so everything which says W1, 2, W3, W4, those are all workers, right? So these are actual physical computers stored somewhere in your institution. And you have a limited set of workers. So it's scalable for sure. It's much more scalable than your local machine. But it's still limited in capacity. Like there is no promise of infinite scalability on HPCs. If anyone has questions, like I can't see the AirMeet platform while I'm presenting, so I'll just wait till the end and take questions. Or when we're doing the demo, if there's any gaps, I'll take questions. So now we'll step into a different approach using Kubernetes. And I want to first introduce a few concepts of Kubernetes and why we're doing it this way. So Kubernetes does container orchestration, right? So what is this container we're trying to orchestrate, which has Bioconductor on it? So what does orchestration mean? Let's talk about what orchestration means first of all. Let's take a step back even more. So orchestration essentially is deployment and scaling or management of a containerized application, such as a Docker image, right? So, and now since I said deployment, management, and scaling of a Docker image, we need an actual Docker image to orchestrate. And Bioconductor has been providing a Docker image for almost 3-4 years now. It's the Bioconductor Docker image, and there's advantages to this image already. It includes all the system dependencies needed to install every package in Bioconductor. It also has an RStudio front end. So there's obvious advantages to using this so that you don't have to struggle to install any single package anywhere. What else does Kubernetes give us? So Kubernetes also makes sure that all the services which are in your containerized application run smoothly. So what that means is it is fail safe. So if your Docker image, which is running on the cloud somewhere, fails for whatever reason, the server goes down, which is running on, or something happens, like there's a hurricane, it's redundant, so it'll spin up again automatically. So it's fail safe. And the other advantage is rolling updates are possible. So as long as you update your Docker image, Kubernetes will make sure that it happens seamlessly. You don't have to stop your cluster on the cloud. You don't have to do anything. You can just do rolling updates. I'll introduce some Kubernetes language here, which is important for the rest of the talk. And if you have any questions about this, feel free to ask. I'll stop for a second. So a node is an actual VM or a compute instance on the cloud. This word node is used very often in Kubernetes. And then there's pod. A pod is the most deployable object or most basic deployable object in Kubernetes. So often a pod is either a single Docker image or a group of Docker images, which you can configure and get them to run in a certain way. And when I say deploy, I mean have it run on the cloud. Let's think about it that way, at least for now. And then there's this word called cluster, which I use a lot. And a cluster essentially means the entire architecture of this Kubernetes application, which is running on the cloud. I'll also say volume mount a lot, and that means some file system or volume storage, which is backing up our pods which are running on the cloud. So any service we provide, we need some sort of backend to store things, and this is a volume mount. And then we have a Helm chart, which is essentially a package manager for Kubernetes applications, just like, say, Bioconductor. Bioconductor is a repository. Helm is also a repository for Kubernetes applications. So I'll just stop here for a second before I move on. I don't see any questions, so I'll keep going. All right, so let's delve a little deeper into this Kubernetes language with the figure. you know what they say, a picture is worth 1,000 words. So this is a Kubernetes cluster, an example of a very simple Kubernetes cluster. So you can see that this cluster here has 3 nodes. Everything in green is a node. A node is an actual VM on the cloud, like a virtual machine in the cloud. So we have 3 nodes here, and we have about 6 pods. And think of a pod for now as a single Docker image, right? So we have 6 deployments of Docker images on this 3-node cluster. Each node is limited by a certain amount of CPU and memory. So let's take, for example, a single node, and it has 2 CPUs and 8 gigabytes of memory. So let's say node 3. So pod 2, 5, and 6 here have to share that 2 CPUs and 8 gigabytes of memory. So this cluster can work seamlessly. And this Kubernetes API at the top is how we control this cluster. And there's a command line functionality for that called kubectl, which lets us control whatever we launch and how we manage this cluster. And there's APIs in other programming languages as well, like R and Python, which we can use as well. So I said a lot about scalability, saying that the cloud gives us a promise of infinite scalability. Let me just hide this guy. Infinite scalability. So let me just talk about scalability and what dimensions we can scale a Kubernetes cluster in. So there's 4 dimensions of scalability, and there's 2 entities you can scale. You can either scale a pod or a node, and that's it, right? So the top half of this figure, I don't know if you guys can see my mouse, but like the top half of this figure is representing the scalability of pods, and the bottom half is representing the scalability of nodes. The top half indicates workloads which we provide to a certain pod, and the bottom half indicates the infrastructure, like the actual virtual machine and the size of the virtual machine which we're increasing. So we're focusing right now on adding more nodes and scaling the number of nodes we have. So think about it as if your cluster is limited by nodes, you can add more nodes to it. You can add more nodes or you can reduce nodes. So you can scale this left or right. And this is a cluster autoscaler, right? So you can add more nodes as needed. The other way you can do it is you can also increase the size of your node. So I said earlier that you have 2 CPUs and 8 gigs of memory. You can increase it to 4 CPUs and 16 gigs of memory, and even larger machines. As long as you're willing to pay more, there's always a node available for you on the cloud. And then you have pods. As the size of the nodes increases, you can have more pods as well. So if you configure your pods correctly, you can add more pods to do more work. Or if your pods need more resources, you can even increase the size of your pods. But essentially where money is being spent is the bottom half of the screen. Anything to do with nodes is costing us money. So that's something we need to be aware of. So those are the dimensions of scalability in Kubernetes. Okay. So we designed a Kubernetes application for Bioconductor users. And I'm going to show you guys a picture of this Kubernetes application and try and explain it the best I can. So we'll talk about user flow a little bit here. And I tried to involve or step through a user's flow with some steps. And it starts usually with a user being in a terminal. So think of yourself as a user. And your first step is you open your terminal and you start a Kubernetes cluster on the cloud. And then you will install this Bioconductor provided Helm chart, which is like a package on this cluster, which you just launched. It'll take a little time for the first step and the second step to happen. Once you're through that, you can connect to the manager pod in your Kubernetes cluster. So now you ask, what is the manager pod? So the manager pod is basically a Docker image with RStudio. This is essentially our Bioconductor Docker image deployed on Kubernetes, and it's being served so that you have access to RStudio, or you can log in via the terminal and use R directly. So that's the manager node. It is very similar to our MapReduce paradigm, where we have manager and multiple worker pods. And you can see that on my node 1, we have manager, Redis, NFS. And on node 2, we have worker 1, 2, 3, and node 3, we have 4 and 5. So this is just an example. It's not like a real life indicator of like what's on what. So you'll see that the worker nodes are running R, and the manager node is also running R, and it is connected to a message passing interface, or like a queuing system called Redis. Redis is basically a queue data structure. So it works as first in, first out. And the manager sends in. So your step 4 is you log into R, you send in some R command. That command gets sent to Redis. And the jobs you send in here are distributed to the workers. So the workers, when they get launched, are waiting for jobs from this Redis queue. So every time a worker is sitting idle and it sees a job on the Redis queue, it pops it off and does the job. And NFS is essentially another pod. This is the server, and this NFS server is serving an NFS volume, which is connected to every pod in this cluster, the manager and all the workers. And this NFS volume is under this read-write many privilege. So every worker and the manager can read and write into this NFS volume multiple times. And all of this is running on the cloud. Any questions so far? I don't see any questions. I'll keep moving. Oops. All right, let's just delve into this user flow just a little bit more. So I spoke about how you can start your Kubernetes cluster, and right now you're able to do this on the Azure Kubernetes service and the Google Kubernetes engine. So Azure is a Microsoft service, and Google is Google, I guess. And you launch this Bioconductor application, which is the configuration is provided to you via Helm chart. You install it, you connect to the manager. And then when I said send work to the workers, we come back to this familiarity of bplapply, which I spoke about. So what that means is you send in a command like bplapply, you give it a list of elements, and the elements can be whatever. You have a function which is designed to work on a single element, and this function bplapply will apply this function to every item on that element. But the BiocParallel parameter is different here. There is a new parameter available for BiocParallel. It's called Redis param. And basically, it is the the package or the interface for the Redis pod, which I showed you guys earlier. Let me just go back to this. So Redis param is what is managing this Redis queue. So Redis param is working both on the manager and on the workers. And then you collect your results, you clean up your cluster at the end of it. All right, so let's get into the demo. I hope this works. So are you guys able to see my screen? I'm guessing you are. So I'm going to go into this folder called demo. I'll just enlarge the screen a little bit more. Make sure you guys can see it. If the screen is not big enough, can I get some feedback from folks? Like, can I get a thumbs up in the chat if the screen is big enough or not? Anyone listening? Okay, I guess it is big enough. Perfect. All right, let's go into the demo. So I showed you guys where the demo or the examples for the Helm chart are available. It's in this location called BioC K8s cluster on GitHub. So I already cloned that repository on my local machine. And I have a few options here. I have two options which work on Azure. So everything prefixed by AKS is working on the Azure Kubernetes service. And everything prefixed by GKE is running on the Google Kubernetes engine. And there's three options here for us right now. The first one works with a volume, storage volume called the Azure file share. The next one works on the NFS volume as the storage. And this Google Kubernetes engine also works with NFS as the storage class. And then we have some example applications. So a lot of this work is in progress. So if something doesn't work, please give us some feedback. So we're going to do the demo today for ease of use reasons, and also just being able to show you guys a quick example on the Google Kubernetes engine. So first, I have to log into my Google Cloud. So I'm paying for Google Cloud through a credit card. So if you guys want to try this at home, you need to have access to a credit card, and you need to be able to sign up for Azure and Google. So first thing, I'll say gcloud auth login, and that's going to log me in to a Google Cloud account. Perfect. And then now that I'm logged in, I can actually launch a cluster. I can say gcloud container. The functions for Azure are also very easily compatible. Like, they're almost similar to what I'm typing on gcloud right now. Create zone, US East, since we're in the US East zone. B, num nodes, let's say 3. And machine type. So I'll explain this to you guys one by one. And I'll just copy this guy from my little cheat sheet here so that I don't make any mistakes. And then the name of my cluster is going to be BioC K8s Redis demo 2. And I'll explain why that is. So this command, what it's saying is, hey, Google, create a cluster for me, a Kubernetes cluster for me on Google Cloud in this zone, which
Sorry, I didn't understand.
I'm sorry about that. That's my Google Home screaming at me. In this zone, and add 3 nodes of this machine type. So the nodes represent virtual machines, and the machine type represents how many CPUs per node I have and how much memory per node I have. And I'm going to call my cluster K8s Redis demo 2. Oops. Container clusters. It's clusters with an S. So that's going to take some time to launch. But anticipating this, I launched another cluster ahead of time with 10 nodes so I can show you guys a demo. So I'll change over to this other screen where I have my second node. But essentially what was done is, so once that cluster was launched, I was able to do something like gcloud container clusters get credentials K8s Redis demo 2, since we just launched the second demo, and give it the zone US East 1B. And that would get the credentials for my Kubernetes cluster. So I know. So what is that command doing? So it's basically telling my computer, hey, work on the cluster, which is called K8s Redis demo 2 instead of like some other cluster. So my previous cluster, which I launched before this session, was called K8s Redis demo. There was no 2 attached to it. So when I say that, it'll give me that cluster, kubectx. It'll say, hey, I'm working on this cluster right now. And that's great. Okay. So the next step of what I did was install a Helm chart. So as you guys saw here in my demo, we have these Helm charts, and each Helm chart, let's take the GKE NFS Helm chart. So you can see that each Helm chart has like a chart.yaml file, some templates, and some values.yaml. I won't get into too much into like what Helm is and so on and so forth. But essentially, all the values you see in the YAML file, in the values.yaml file, are configurable. So you can actually change, but you can actually change all the user-oriented configurations here, and it'll do that thing for you. The rest of them you don't have to worry about. So you can launch this Helm chart by saying Helm install K8s cluster, the name of the cluster, and you can set a worker pool size of say 50 or 100 or whatever number of nodes you're based on. So since we launched 10 nodes in this demo, I launched ahead of time, I'm going to say 50 pods. So the worker pool size is giving me the number of pods. And then I can also say, I can also set the BIOC version. So if I wanted to work on a cluster which was running on BIOC 3.13, I could say BIOC 3.13 as the BIOC version. And I also need to set a corresponding image tag, which is called worker image tag, and say release 3.13. So this is actually giving us which Docker image to use, and then point it to the Helm chart, GKE Helm chart NFS, and then say wait. So what that will do is deploy the Helm chart on this Google cluster which we just launched. So this also takes a little bit of time, about like 2 to 3 minutes. So in the interest of time, I did this ahead. And I have a Helm chart, Helm status, Helm status, I guess. Oops. Helm status, K8s Redis demo. So I deployed a Helm chart already. Apparently not. See, did I misspell it? List. Oh, apparently there's nothing here. kubectl get all. Okay. Apparently there is no Helm chart deployed. kubectl get all. This is what happens when I'm doing a live demo. Give me one moment. Cube. So you can see here that our second cluster launched. So maybe we can just go with that. So that's a good thing. Since we launched 3 nodes, we can try this. We can say Helm install K8s Redis demo to worker pool size 10 and actually launch this Helm chart and wait for it. Okay, I think what happened was the context got switched, but we can fix that. While we wait for this, let's go back onto our other terminal session and kubectx. I see. The context got switched. kubectx. kubectx is switching context. I don't want you guys to worry about this. This is supposed to be a simple demo. So now we'll go on to a larger cluster, kubectl get all, and that will give us give it 1 second. There we go. So we have a running cluster of a manager node, a manager pod, and about 50 worker pods running on the Google Cloud. And we also have RStudio running. We have this NFS server running. We also have the Redis server running, and everything is available for us to use. So let's log in to the manager pod to actually do some work. So I'll say kubectl exec, just like Docker exec, and then give it the name of the manager pod, which I just got from above, and log in with bash. So I have a Kubernetes cluster here with me. And just to demo a very simple thing. So this host location is where the NFS volume is sitting right now. So you'll see that the NFS volume has 2 files right there, index.html and lost and found. And this is connected to all of our worker nodes as well, worker pods as well. And there is another location, home, RStudio. This is where all the files local to your RStudio are being stored. And I wrote this little script called manager demo.r. And I want you guys to focus on this, maybe I should say set number, line 6 here. And what line 6 is saying is, once I call Redis param, I can go to line 6, say Redis param, set the number of workers to 50, give it some job name. And is this node the worker? It's not, it's the manager. So I say false. I write a simple function. All it does is sleep and print out the node on which it's working or the pod name. And then I apply a simple function here, the sleep function. 100 times. So since we have 50 pods and we're doing the job 100 times, so we should sleep exactly for 2 seconds. Let's give this a go. And I'll go into my R and I'll say source manager demo echo equals true, max equals inf. And it's sourcing the script we just wrote, and then it prints out the result of the system.time. So you see that it didn't sleep for 100 seconds. It slept exactly for 2 seconds. And you can see that here. Time elapsed is about total 3 seconds. So there's a little overhead. But each worker pod slept for 2 seconds. And you can see the node name, the host name for each of these workers is different. So you can distribute other jobs like this as well. So I wrote this simple like pi approximation function. It doesn't do much. If you give this function some big number, it'll compute an approximate value of pi for us. So the larger the number, the more close the value of pi becomes. And I've already declared my Redis param, and I can say res, or rather, let me say val, bplapply, rep. Let's give it a large number like 10e the say 6, 10 times, and pi approx bp param equals p, because that's what we call our Redis param, and that should compute a value of pi for us. So it computed this 10 to the 6 is what? A million? 10 to the 6 is 10 million. So 10 millionth number value of pi, and it'll give us like, and it did it 10 times. So you can see that the mean of this result will be a very close approximation of pi, 3.14, and so on. So essentially, this shows us that we're able to distribute our work to multiple workers. And so that's it for the demo. You still have to shut down your cluster by saying something like gcloud container clusters clusters delete K8s demo, and you can delete your cluster on the Google Cloud, and that'll just work. So we'll go back to our demo one more time, and hopefully get through the session pretty quickly. So what is one of the applications of this Kubernetes cluster? We're currently using it within Bioconductor to build Bioconductor binaries. We're doing it both on Azure and Google Cloud, but going forward, we're going to build it more frequently on Azure. And how do we do this? So we compute this package dependency depth-first search graph, and each level is a list of packages with the level number of dependencies. So level 0 is around 500 packages in Bioconductor which don't have any dependencies. And then level 1 is about 300 packages which have 2 dependencies. And so 1 dependency. And then level 3, for example, is about 300-ish or so packages too, with 3 dependencies. So if D is a package, B, A, and S are the dependencies of D. So we distribute each level to multiple worker pods through Kubernetes. We use the exact same application I showed you. And we store the built binaries on an object store. On Azure, it's the blob container. And on Google, it's the Google bucket. And we distribute it via the URL, which is provided to us by Google. So that's a application which is currently in use, and it's being distributed very successfully. So again, I want to go over the availability. Right now, it's available on Google and Azure, but in theory, you could use these Helm charts on other clouds as well. So the advantages, as you've seen here, is like it's pretty on demand. So I scaled up this like massive cluster in front of you guys with a few keystrokes without doing much. It's very customizable. You can change what volume you use. You can change how much CPU each pod is using, and so on and so forth. It also allows rolling updates to deployments. Right now, we allow we have tested it successfully, and we're using it successfully in both GKE and AKS. But there's no reason you guys can't launch it on whatever cloud you want. Oops. So this still remains, like some parts of this remain a work in progress. Redis param is still a work in progress and has multiple moving parts. We have Docker images which are getting updated to make them simpler. These Docker images are called Redis. They're available on Docker Hub. We're also working on horizontal pod auto scaling, which is a different dimension of scalability than just scaling the nodes. We have a couple of RStudio issues which we need to fix. And there's working examples of non-bioconductor solutions. So you can customize this Docker image with a non-bioconductor bioinformatics software. You can install it on that Docker image, and you can use this in parallel as well. Finally, I want to thank a bunch of people, Martin, Jeffe, Vince, Rafa, and the entire Bioconductor core team. So if you have any questions, I'll take them now. That was a lot, guys. It was, so I probably should have submitted it as a longer talk. I couldn't squeeze everything I wanted to say in a small talk. But there's a question here. It says, any reason why not in AWS? You can deploy those Helm charts in AWS without any problem. There shouldn't be any difference. What would happen if a worker exceeds its resources? And could I have Linux and Windows workers in Azure? So I can answer, I guess, most of this question. So if a worker exceeds its resources, it'll just go into a pending state or a crash back off state, and the pod won't launch. So if you check your Kubernetes cluster, it'll show you that that pod, for whatever it is, for that memory reasons, hasn't launched. And you can scale it appropriately and redeploy, and it'll work just fine. You could have both Linux and Windows workers in Azure in theory, although I've never done it. I know someone in the audience from Microsoft Genomics who might be able to answer that question, but we'll probably like wait a second and see if we have any more questions. Okay, if not, maybe we can ask, yeah. If there's no other questions, like we can end the session and see if we can get an answer from the folks over at Microsoft Genomics. I know Erdal is in the audience. But okay, yes. apparently we can have both workers. We can have workers both in Linux and Windows in Azure. Yes. Thank you so much. Yeah, that's all I have. Thank you guys for listening. I know it was a lot in a very short space of time. It's a complex piece of software, but it's evolving, and hopefully it'll be in a user-friendly, usable state very soon. And we'll have some examples in that GitHub repo so that people are able to use it and by following the examples. I guess that's it.
Thank you so much, Nitesh. Maybe you'll
Thank
give
you.
us an update at BioC 2022 for the next version of this next
Yes,
year.
hopefully. Thank you so much.
Thank you, everybody, for joining. We still have another workshop session right after this, and then, of course, the closing ceremonies at 10:45. That's Eastern time. So we hope to see you all there. Bye.
I'll grab some dinner now.